area. Okay. So this question is slightly different. It's asking for the area between the x-axis and the curve. So what does this area look like? Okay, it's between -1 and 1. So what does 3 secant squared 3x look like? Okay, it's basically going to be a secant graph, okay, that has been secant squared graph, which has been vertically expanded and horizontally compressed. Okay, so I think when x is 0, okay, we're going to end up with secant of 0 is 1 times 3. So basically we're going to have something that looks like this. And when x is equal to pi over 2, ooh, this is going to be a little bit tricky. So when x is equal to pi over 2, okay, or the angle is equal to pi over 2, so this is going to be here at pi over 6, we should expect a vertical asymptote. Okay, and then it's going to continue like this, something like that, and that's going to be at pi. Okay, so we are going to look for this graph. This is an improper integral. Okay, so it's going to be 3. I'm just going to double check this by graphing this. I'm just going to make sure that I know what I've got here. Divided by cosine 3x to the power 2. Okay, so the graph that I've sketched there looks pretty much what I'm dealing with here. Okay. Oh, looks like we've got way more asymptotes in there. Okay, so sorry, I've miscalculated my compression here. So that's going to be pi over 6. Is going to be the first one. Okay, and we're going to have a period of what's that going to be? 2/3. So looks like there's going to be a vertical asymptote. Okay, it's going to look like this. Vertical asymptote right about here. And that asymptote should happen at what value is going to have that happen at? Okay, we're going to have another one here. So we're going to be, ooh, this is kind of a bit of a messy one, so we're going to have to take our time doing this. And so we should have about 1, 2, 3 asymptotes, and then it looks like right about there is going to be 3. Okay, so I just sketched this on my graph. There it is. Okay, I really should figure out those parts a little bit more concisely, but that's going to be, looks like it's 2/3 pi, so it's going to add 2/3 pi to that. Okay, so that's going to be 5 pi over 6. Okay. Okay, so there's going to be, yeah, that looks about right. Okay, so that's going to be not 5 pi over 6, but pi over 2. Okay, we're going to add 1/3 pi there. So pi over 2, and then this asymptote here is going to be at, we're going to add another 1/3 here, so that's going to be the 5 pi over 6. Okay, and looks like that's going to be that point there. Okay, so there's our graph. I think what we'll do is we're going to find the area underneath the curve here. Okay, and we can find that area and say that this area is going to be half of it. So we can have call this area A, that's area A, that's half A. And then once I figure out A, I just need to figure out this area in here, which I'm going to call B. Okay? So I'm going to use some symmetry to save a little bit of work here. Okay, where's my area? What happened to my area? Okay, there we go. Okay, so I'm going to start with the red area here, which I'm going to call A. Okay, and we're going to anti-differentiate this. Okay, so I'm going to call that area A, and that's going to be the limit as, actually I'm going to find area of half A, because that way I don't have to worry about two different limits. Okay, so I'm going to start at 0. It's going to be limit as A goes to pi over 6 of the integral from 0 to A of 3 secant squared 3x dx. Okay, so I'm going to work out that limit first. So this becomes the limit as, so this, the antiderivative of this is going to be tan 3x divided by the 3. So we're going to end up with the limit as A goes to pi over 6. And it's going to be tan 3x, or I'll write it as 3 tan 3x divided by 3, so 3's cancel out from 0 to A. And then I'm going to plug in the A value here. So I end up with, I'll rewrite this, limit as A goes to pi over 6, and 3's cancel out, of tan 3x from 0 to A. That works out to be tan of pi over 2 minus tan of 0. Okay, so tan of pi over 2 is infinity, and we're approaching it from the positive side. I should write from the positive side, so it's going to be going to positive infinity minus 0, so we end up with positive infinity. Okay, so the area, the half of the red area there is going to be infinity. So if half A equals infinity, we can say that A is equal to an infinite area. Now we really don't need to figure out B, because we already know that that total area is going to be infinite because we have half A, half A. Okay, those are all infinite areas, but we'll just do B anyways. We'll just set this up properly. It's good practice for our improper integrals. Okay, so I'm going to say that the area B is equal to the limit as A goes to 5 pi over 6 from the positive side. Okay, because I'm approaching that from the positive side this way. Okay, that's my area boundary, and it's going to be from A to 3. And that's going to be for 3 secant squared 3x dx. Okay, this is the same integral as before. A goes to 5 pi over 6 from the positive side. I'm going to end up with tan 3x from A to 3. I'm going to evaluate that limit. I'm going to plug that in. So I'm going to end up with tan 9, okay, minus tan of, when I plug x in there, I get tan of 5 pi over 2. And then approaching it from the positive side, and that works out to be 5 pi over 2 is going to be, did I do that right? 5 pi times 3 divided by 6 is going to be 5 pi over 2. Yeah, that's right. Okay, so I'm approaching it from the positive side. Okay, so if I approach that from the positive side, that's going to be equal to negative infinity. Okay, so if you imagine the position of that circle, the position of that is going to be vertical here. Okay, as I approach it from this side, my slope is going to be negative infinity. Okay, so I get tan 9 minus negative infinity, and again that area is infinite. Okay, tan 9 minus. So area under B is also infinite, being an unbounded integral. So that example there actually really wasn't the best example because we really didn't see areas above and below the curve, but that's actually a very good practice for dealing with improper integrals.